Okay, it's time to start the second talk in this session. As you know, this year is a remarkable year. We are celebrating, as we see the top line, 120 years of the birth of one of the greatest mathematicians and probabilists, Andrei Nikolaevich Kolmogorov. Maybe for our guests of the conference, it is not so well known that there is a direct and indirect and very serious and efficient influence of both Andrei Nikolaevich Kolmogorov, him, and also his former students, his former collaborators. So there are people who are, I'm using the term academic great children, great sons or great daughters. And so some of them are here, and one of them, quite remarkable person, is our colleague, Nikolai Yanev. So let us invite Professor Yanev to come to the stage and give his talk. The title is there. I don't need it. So, welcome very much.
First of all, I would like to thank the organizer for this very nice and useful conference, I hope. Okay, as you can see, our paper is dedicated to the University of Kolmogorov. Kolmogorov was born on 12 April, new style, all 24 is old style. And I will say later a few words. This is talk based on some joint papers with my co-authors, Marusia Savcheva-Boshko from Sofia University, Olivier Irian from Fred Hutchinson Cancer Research Center, USA, and Kostomito from Medical University from Bulgaria. By the way, do you recognize this person? Yeah, this is the portrait of Kolmogorov, just from my office. He is always with me. And here we can see three of the selected papers, books of selected papers of Kolmogorov. This is Mathematics and Mechanics. This is Probability and Statistics. And this one, Information and Algorithms. By the way, this first, this is also the portrait of Kolmogorov, and started with one thought of Kolmogorov. I will try to translate from Russian, but it's something like this. In all my life, my first rule was the truth. Our duty is to discover the truth and to fight for the truth. And this is really Kolmogorov, because he was not only a great mathematician, but also a great person. And okay, everybody knows something about Kolmogorov, but I'm not sure that someone knows everything for Kolmogorov. So let's remember some of the major topics of where Kolmogorov has a very deep results. First of all, trigonometric series. It's as a student, first year old, he discovered really very deep and interesting things in the trigonometric series, and very popular is his example of integrated by Lebesgue function, which Fourier series is not convergent everywhere. And after that, he has very deep papers in the theory of set, measures, and integration, approximation theory, constructive logic, topology, and geometry, functional analysis, theory of superposition, and he solved Hilbert's 13th problem. Then in cohomology theory, topics in classic mechanics and Gaussian theory, the dynamic system theory, turbulence, diffusion equation, foundation, and the probability theory, as we know, and then solved Hilbert's 6th problem. Theory of stochastic processes, we know Markov, stationary branching, diffusion, and so on, limits theorem, mathematical statistics theory, algorithms, information theory, application in nonlinear quantum mechanics, physics, mathematical geology, biology, genetics, social sciences, articles on the theory of poetry and statistics of text and literature, papers on the history and methodology of mathematics, and the teaching of mathematics in schools also. And as it was written in many journals, Kolmogorov was really the last encyclopedist in the field of mathematics. And he really created many scientific schools which are needed for most of his peoples. He has about just 71 PhD students, and most of them are very, very popular all over the world. Okay. In 1938, Kolmogorov published 19 works. Between them, one book, 13 papers in journals, 5 articles in encyclopedia. 19 works for Kolmogorov is not an unusual thing, because he has more than 800 works. And between them, one very interesting paper on the solution of one biological problem, with only 2 references. One of them are of the Fisher, by Fisher, the genetical theory of natural selections, yeah? And the other one is Stephenson, the problème du calcul des probabilités. And Kolmogorov considered a biological problem really posed by Fisher about multiplication in a new gene in a population. And he intended to answer to the real question of the Fisher. It's necessary to know not only the probability of extinction, but also the asymptotic probability of non-extinction. And he obtained in this case the first asymptotic result in the theory of branching processes. By the way, at that time there were not branching processes, because Kolmogorov imagined this terminology later. But Kolmogorov interested, in fact, not only in mathematics, but also in science That is why he read this book of Fisher and also many other books. And I remember that he invited his seminar many specialists in the fields of physics, biology, geology, and so on. And I was very much surprised as a PhD student in Moscow State University that Kolmogorov understands very well everything in these areas, and even more than the lecturer. Okay. So let's see now just the problem which solves Kolmogorov in this paper. So let x be an integer random variable and x it be a set of IID copies of x. Then the classical BNMA Galton Watson, they were presented here by Professor Griment, and is defined by this reference, well known, where x it plus 1 are the offsprings of a particle existing in the t generation. So they are offspring in the t plus 1 generation, and the sum of this offspring in t generation given as t plus 1 generation, and so on. So for zt is a Markov chain, and very important, 0 is an absorbing state. And if m offspring b is less than 1, it is a critical case. Or if m is equal to 1, we say critical case, and then in this case there is extinction with probability 1. And if in the supercritical case, m greater than 1, the probability of extinction is less than 1. We say that there is no extinction. And Kolmogorov obtained asymptotic behavior of the probability of non-extinction, and especially in the critical case, he considered all cases. In the critical case, this is this famous result that in the critical case, if the offspring variance is finite, this probability of non-extinction is asymptotically equivalent to the Kolmogorov constant divided by t, where k is just 2 divided by sigma square, offspring variance. So the aim of our talks is to present the asymptotic behavior of the probability of non-extinction and also some limited theorem for more general classes of branching stochastic processes, from which this BNMA-Galton process is a particular case. We will consider two classes. One of them is one-dimensional, but not Markov and non-homogeneous in type. And another will be multi-type Markov, also non-homogeneous. Okay. Some more about the history. In 1940s, Kolmogorov started to interest of nuclear processes, and in 1946, Kolmogorov organized a special seminar on branching processes in Moscow University as possible branching processes, possible models of nuclear reactions. Some really fundamental result had been obtained by him and his PhD students, which really created the base of the modern theory of branching processes. These famous seminars worked many years, and later worked the leader of the seminar was Sebastianov. And when I was PhD student of Sebastianov, and I had a chance to be a member of this seminar, it was only 50 years ago, at the beginning of the 1970s. Okay, the terminology branching processes was introduced by Kolmogorov in 1940s, but officially appeared in this paper, Kolmogorov and Dmitriev, branching random processes. And the second paper, Kolmogorov and Sebastianov, in this paper, the first papers, really for the first time was construct multi-type Markov branching processes and corresponding equations, some basic results. And after that, this paper of Kolmogorov and Sebastianov, and paper of Yaglun, also PhD student of Kolmogorov, with very popular limit theorems. And all these results and many others were summarized in Sebastianov for this book, Branching Process, in 1971. I had the chance to read manuscript. I was the last to read the manuscript. There were some errors. That's why when the book appears, Sebastianov gave me the first copy of a photograph. It's a very special book for me. Okay, I'd like to say something about the co-author of Kolmogorov, on the first famous, okay, no, okay, Kolmogorov, Dmitriev, PhD student of Kolmogorov. At the age of 23 years, he was adapted as a research assistant in the special secret town of Sarov about the uranium project. And he collaborated with Sakharov and became one of the main creators of the Soviet bomb, applying branching processes and many other things. By the way, he was a very unusual person and wunderkind, real young genius, because in 14 years old, he won the mathematical Olympiad in Soviet Union. 14 years old, and he was student, started at 14 years course, 14 years as a student in Moscow State University and finished in 17 years. And then Kolmogorov, and after that he was a PhD student of Kolmogorov in Steklov Mathematical Institute. So he was just as Oppenheimer in USA, and Dmitriev, of course, his collaborator, was the leader to create this nuclear bomb. I describe a paper, this one, in the memory of Dmitriev, with he was very interesting history. By the way, he is Bulgarian, with a very famous Bulgarian family. So if you are interested, this is the link. There is many interesting positions. He was
Professor Yanev, there is one small mistake. You have two initials to change in reference 7.
This one?
Yeah. No, the author.
This is...
yeah, NM.
Yeah, this is... okay.
It must be
Excuse me. NM.
Nikolai Mikhailov.
Yeah, excuse me. Okay, yeah.
Yeah,
Thank you.
yeah.
Yeah. This is, yeah. So he was not only mathematician, but also he has a very deep result in the physics, and physicians said that he is a physician, and mathematicians said, oh no, it is a mathematician. So it is really very an ordinary person. He has about 30 publications which are open, and they say that about 100 which are secret up to now. Okay. So I would like to point out that the first model of non-Markov branching process was introduced in 1948 by Richard Bellman and Theodore Harris. They introduced the so-called age-dependent branching processes, where particle evolution tau mu is described. The lifespan has some distribution function, and nu is the offspring of the one particle. And if this distribution is exponential, then we have Markov branching process. In other case, the process will be normal Markov. And then Sebastiano generalized this model in the case when tau and nu could be dependent in this paper. And in the Sebastiano process, the particle evolution is described by this way, where P and X is the probability of one particle to produce n individuals if the mother life is just X. In this case, we will obtain Bellman-Harris processes when this tau and nu are independent. Okay, let's now introduce multi-type Markov branching processes with immigration generated by Poisson random measures. Let T1, T2 do not the time generated by Poisson random measure with local intensity R of T and mean measure R capital of T. Then it's well known that we have this formula just for our students which are here. And let Ik be a vector of IID non-negative integer varied random variables with this multi-type probability generating function. And then we consider the mark point process, Tk, Ik, where the vector Ik will be interpreted as the number of immigrants that join the population and time Tk. So define the multi-type branching process independently, Z, where Zijt denotes the number of type J individuals, or cells, or particles, at time T, produced by a single type I individual, born in time T equal to 0. And assume that the individuals evolve independently of each other. It's very important. Let Fi Ts be the corresponding multi-type probability generating functions for type A, and F is this vector. Okay, let's now consider Z tilde will be the process which start now with this random vector, random number of ancestors. This process starts with one ancestor of type I, and here we have a random vector as of for ancestors. It means that in fact probability generating function of this Z tilde is just J of FTS. This is F, and J is the probability generating function of immigrants. We assume that Z and P and Poisson random measure are independent. Then we define the process YT by this formula. In fact, the process starts when appears first group of immigrant at time T1, and from each immigrant start branching processes. So this can be considered as some superposition of branching processes. In time T appear the second group of immigrants, and from everyone started of one branching process, and then we refer to this process as multi-type branching process with non-homogeneous Poisson immigration. Okay, this model finds application, I will say later. Study evolution of multi-type cell populations, where new cells join the population according to time varying immigration mechanisms. And very often these stem cells appears as immigrants in this case. Okay, this is the first theorem which represents the probability generating functions of the process with immigration, where he is the probability generating function of the branching process. This is a general formula for any kind of branching processes with independent evolutions. This theorem is produced in this paper. And process with independent evolution as considered in many monographs and include multi-type Markov branching processes, Bellman, Harris, Sebastianov, or Krupp-Mott-Jaeger branching processes, and many others where individuals evolve independently of each other. And these are described in these very well-known monographs. Okay, let's say something about the history of these processes. Sebastianov was the first who introduced this model with immigration in the case of single type continuous time Markov branching process, when the time of immigration form homogeneous Poisson process. Then Jaegers generalized this model to Bellman Harris branching processes, and the people who work in this field. And Sebastianov branching processes, but with homogeneous Poisson immigration was considered by me. And Now we will consider Sebastiano branching processes with non-homogeneous Poisson immigration. Note that this process is non-Markov and non-homogeneous in time. Okay, something about the history of different model of branching process with non-homogeneous immigration. In this paper, we consider discrete time branching processes, but even with non-homogeneous migration, it means that not only immigration, but emigration also. And there is some other papers, but I will present our result in the end of the presentation. So let's consider now single type Sebastiano branching process with not homogeneous Poisson immigration, where we have this general formula, but where now the probability generating function f satisfies this non-linear integral equation. Sebastiano discovered this equation first and proved that this equation has unique solution in the class of probability generating functions. So here J is distribution, the line distribution. X is the offspring distribution when the life of the mother is X, and let Js is the probability generation function for immigrants. This is the mean, the second order moment. This quantity is like general mean of the process, not independent of the age. B, second order moment, general, and is the mean of the lifespan, and this play also very important. This mathematical expectation play also very important role. Gamma is the mean of the immigrants, and let C be this constant immigration, here reproduction, and this is also reproduction. So, and we will investigate the probability of non-extinction in this case. Yeah. Okay. And we have the following asymptotic result. In the critical case, when this, just a moment. Okay, right. Where A is something like mathematical expectation non-dependent of X, and when it is less than 1, it is subcritical case, A equal to 1 critical case, and L greater than 1 supercritical case. So we will consider only critical case. And C was this constant, which we say. And first condition, if R is finite, R capital is finite, and local intensity of Poisson measure is satisfy also this condition, then the probability of extinction is similar to those obtained by Kolmogorov, constant divided by T. In fact, in the case of being a Golden-Watson process, C is just equal to the Kolmogorov constant. If R of T, intensity of the Poisson measure, is slowly variative function divided by T, then we have this asymptotics, where L star is this slowly variating function, especially if LT converges to some constant, then this slowly variating function is just 2R multiplied by log of T. In the case when RT is regularly varying function with parameter theta between -1 and 0, or even theta equals to 0, but this slowly varying function is small O of 1 divided by log T, then we obtain these asymptotics. And finally, if this is regularly varying function with parameter theta greater than 0, or even theta equal to 0, but LT converges to some constant, then the probability of non-extinction converges to 1. It means that there is no extinction in this case. Okay, so we call that this was Kolmogorov approximation of the probability of non-extinction in the Markov case, when 0 is an absorbing case. But in our case, 0 is a reflecting barrier. So this is the probability do not hit 0, or decay of non-extinction. In all these cases, we obtain different type of limit theorems, but now I would like to present you only one of them, which maybe is the more interesting. So, in the critical case, where R of T, Poisson density, is slowly variative function divided by T, and in the case when this LT multiplied by log T and divided by R of T, mean measure of the Poisson measure, if this limit is rho between 0 and infinity, or even 0 or maybe infinity, then as T converges to infinity, the process YT with two different normalization, we obtain two limiting distributions. We are singular to each other. The first one, if this is C1 is this constant multiplied by T, then we obtain exponential distribution. We have an atom at 0, which is rho divided by 1 plus rho. But if we consider log of the process divided by log T under the condition of non-extinction, then the limiting distribution is uniform distributed with unit interval with an atom at infinity. It's a very strange result for me. I have no explanation, but we can interpret this result that with probability 1 divided by 1 plus rho, the growth is linear, where psi is exponential distributed random variable, or with probability, which is rho divided by 1 plus rho, the growth is parabolic, where eta is uniformly distributed on interval 0, 1. Especially if rho is equal to 0, then we have pure exponential distribution in the first case. Or if rho is infinity, then we have pure uniform distribution or the unit interval in this case. I have no explanation for this result. It's very strange for me. Maybe we have to. Okay, no. No, what happened? Okay, maybe in this case these are long-lived particles, but in another case are short-living particles, and then divided into two groups. But I'm not sure that this is the correct explanation. Okay, let's now consider a multi-type Markov branching process with non-homogeneous Poisson immigration with this intensity for all possible values of theta. And we assume now that every particle or cell has exponential lifetime distribution, and this is the offspring probability generation function for type I. And now the process Z is a multi-time Markov branching process and satisfies these equations, forward and backward Kolmogorov equations, where F is Fi are infinitesimal generating functions. Okay, so under these assumptions, YT is multi-time Markov branching process with non-homogeneous Poisson immigration. So let's now consider some basic notations. First of all, the matrix of first infinitesimal characteristic, matrix A, and then these are the second order infinitesimal characteristics. Assume that this matrix is irreducible. It means that all types form one class of communication. And let rho is the Frobenius root of this matrix. And we have left and right eigenvalues with this typical condition. This is offspring, this is immigration means and immigration second order moments. And this will be our basic condition. We assume that the local characteristic of reproduction of immigration are finite. Define this constant C, Fk multiplied by right eigenvector, eigenvalues, and let B this this sum, left eigenvalue, this second order infinitesimal characteristic, and array eigenvalues. We will consider critical case when rho is equal to 0. When rho is less than 0, it will be subcritical case, and rho greater than 0, supercritical case. Then we obtain the following result. Okay, if parameter theta is positive or equal to 0, but with this condition, then we have that the probability of non-hitting 0 converges to 1. It means if the process goes to infinity with probability 1. If theta is equal to 0 with if additional condition, then the probability of non-hitting 0 is between 0 and 1, and just 1 minus e to the power minus gamma, this constant. If theta is between minus 1 and 0, or theta equal to 0, but with this condition, then we obtain this asymptotic of non-extinction. And if theta is minus 1, then the probability of non-extinction has this asymptotics, where this slow logarithmic function is presented in this way. And finally, when R is a constant, final constant, and with this additional condition for this local intensity, then we obtain a result which is just similar to the classical Kolmogorov asymptotics. And even in a particular case, when we have only one type, then this C is just equal to C is just equal to the Kolmogorov constant. And in fact, Q of t converges to 1 if this condition is held, or converges to some constant when this condition, and finally converges to 0 if we have this condition. These are these three cases. Okay, in all of these conditions, we obtain different types of limit theorems. Okay, further on, we will use this notation for limiting distribution, where all components of are almost surely equal to each other. It means degenerate multi-type distribution, where the components are equal almost surely. So in the first case, when this condition holds, then we obtain that the process divided by b of t. This is left eigenvalues. And under the condition of non-extinctions, converge to some limiting distribution d of x, where C1 or any one of the component is just has exponential distribution. Okay, in this case, this is similar to the Markov branching process without immigration, because really in this case, the immigration converges to 0, so it is normal to obtain such result. Okay. When the local intensity is regularly varying with exponent theta positive, or theta can be equal to 0, but this slowly varying function to converge to infinity. Then we obtain that the process normalized by mathematical expectation converge to 1 in probability. So it is similar to law of large numbers. But if theta is greater than 1, or even equal to one of these additional conditions, then the convergence is almost sure. So we have something like strong law of large number. And we obtain the following limit theorem. The process normalized by his means and divided by square root of the variance converge to a vector where multi-type vector where all coordinates are normal distributed 0, 1. So this is like central limit theorem for this process. And we can obtain the following asymptotic normality, especially in the case where theta is equal to 0, LT converges to infinity. We have that the process normalized by this normalization has asymptotically normal distribution with means 1 and this variance. Okay, if we have that now intensity is slowly varying function, if converged to some constant, then we obtain as limit multi-type distribution where all components are gamma distributed with these parameters alpha and beta. If LT converges to 0 with this condition, then we obtain with this normalization as limit exponential distributed components of this multivariate distribution. If we have this condition where alpha is some positive number, then log of the process divided by local t converges to this distribution where components has this special distribution. And if we consider under the condition of non-extinction, we obtain as limit just exponential distribution on the unit interval. Okay, if this is regularly varying function or exponent by in the interval minus 1, 0, or even 0 in this condition, then under this normalization, now we obtain limiting distribution where all components are uniformly distributed on the unit interval. Okay. And in this case, we have with this additional condition, we obtain some result which is similar to the one-dimensional case for Sebastianov branching processes, where limiting distribution, the components here are their H1 and H2 are singular distributions with each other. In the first case, we have uniform distribution on the unit interval with an atom at infinity. In the second case, we have exponential distribution with atom at 0. And we have this interpretation, and it's the one-dimensional case. Okay, one can interpret the local intensity as a control function. Then the asymptotic level behavior depends on this control function, very essentially as we obtain. Okay. In some cases, we obtain this, and the results are similar to the process without immigration and with immigration, and so on. But then new effects as law of large number control in central limit theorem. Open problems to investigate the asymptotic behavior of the multi-type age-dependent branching processes arising by a pause on random measures in all subcritical, critical, and supercritical cases. These are our papers concern single-type Sebastianov branching processes. I present you only critical case, but we consider also supercritical and subcritical cases. This is critical case. These are our papers for multi-type branching processes with non-homogeneous Poisson immigration, critical case, supercritical case, and subcritical case in submission now. These are some papers concerning branching processes and evolution of cell populations. Okay. These are some other persons. Finally, I would like to say that in our body there is 30 or 40 trillions of cells, which are about 200 different types of cells and have different structure, size, and so on. And they are divided, developed in our bodies now, and a lot of branching processes, real branching processes now are in our bodies. And this is a very interesting area for application of branching processes, and we have really some real applications. And okay. Branch me forever was the slogan of the first World Congress of Branching Processes, which was in Bulgaria in 1993, only 30 years ago. This was the publication of the proceeding of this conference, and thank you very much for your attention.
Okay. So first, thank you, Professor Young, for your talk given so enthusiastically. There are very good reasons for Professor Yanov to talk this way. We all know about his great contribution. He's a well-recognized contributor in this area. And I think this topic is appropriate for the event, for the conference, but also is very appropriate about the anniversary of the birth of Andrei Nikolaevich Kolmogorov. Now you can make some comments and to ask some questions, if you wish. before closing, I can tell something in addition to what Professor Yanis mentioned. Kolmogorov has told something which is very important, and this is about the values of the probability theory. And his saying sounds this way: the epistemological value of probability theory can be revealed only or mainly by limit theorems. And in fact, this talk today is another confirmation about something about the deep meaning of what we do, and also the relation to the nature. So it was mentioned, and we know that Kolmogorov was very well familiar with our nature, with all the processes, dynamical, random, etc. And he was formulating and some hypotheses, even proved that many, many years after his death. Of course, there are some other books, and all these books are translated into English language. I've read a couple of books more than this. What is important only this to mention, so in Russia they have already a series of events to celebrate this year, 2023, so 120 years of the birth. I think some 10 days ago there was a special session of the whole Academy of Sciences, the Russian Academy of Sciences, and then there will be a series of special talks. I will be speaking online on Zoom after a week. But in Moscow there will be it is in person, face-to-face events, but we cannot go there. So thank you, Professor Yanis, for your talk, for your work to prepare this huge material. And we are just maybe 1.5 minutes behind the schedule. And because assuming that we are a little tired, now we can rest a little and drink some tea. So let us applaud at him. It's time to continue our serious work. We have our next speaker, it's Boriana Rachka. So let us.
Thank you. Thank you so much to the organizers for inviting me, and it's a pleasure and an honor for me to be here, and I must say a bittersweet feeling for me to have such a presentation, as probably I was not able to present on any kind of theoretical concepts for at least the last 7 years of my professional career. But in any event, I'm so glad to be here, and I hear the event is unfolding like a very strong one, so I trust that it will provoke future collaboration. And I'm here actually today exactly for that reason, to seek collaboration. Why? Because I come from the industry. Although I started as a professional in the field of mathematical finance, gradually I moved to the business side. And for the last approximately 2 years now, I'm leading the buy-side strategy for FactSet Research Systems. FactSet is an S&P 500 company. We have revenues of approximately 1.7 billion. And we serve the entire spectrum of the financial community, starting from the investment banking up to the and ultimate investor on the buy side, which could be pension funds, sovereign wealth funds, and the like. So my responsibility is to make sure that we'll invest for the future in order to serve the buy side industry in the best possible way. So that means that the field that we are here to share about, the field of stochastic processes and Levy processes, is one tiny fraction of all the plethora of the fields that we need to study and understand how to apply. Nevertheless, I trust that it's a field of significant importance. And that is also why I'd like to share with you today some of the latest applications, and possibly we can find together a path how to make them a better part of what the world of quantitative finance is today. So let me start by introducing the three topics that I will speak about today. I will first provide an overview for you as to how fact-tailed models have been currently implemented for financial modeling applications, and applications that I must say are already more or less adopted within the realm of the financial industry. So the first topic is what is out there that work in practice and what are the limitations. The second topic I will cover today is how to make the bridge between behavioral theories and rational finance, i.e. the theory that is behind all the quantitative modeling, the theory that allows us to build all the nice models around pricing derivatives, constructing optimal portfolios and so forth, and we'll discuss briefly as to why this bridge is necessary. And the third topic I will cover today is how to model exogenous factors, factors that have not yet been priced by the market participants. Such factors could be of political nature, such factors could be climate-related, sustainability investing-related, or others. So let me start with what is currently more or less adopted within the financial industry, and I'm saying, when I say adopted, I mean adopted by the innovators. So nothing is kind of standard yet, unfortunately, although you recognize that those developments are absolutely not new from the standpoint of the academia. So the financial markets exhibit several phenomena which makes them very suitable to be modeled through fact-tailed distributions, or when we speak about processes, Levy processes. And those phenomena, again in a synthesized way, are first of all high probability of extreme events. When I say high, of course I mean higher relative to Brownian motion. We also have, however, volatility clustering, i.e. periods when the volatility on the market stays high, then followed by periods of prolonged low volatility on the market, something that we cannot capture with Levy processes, so we'll need something external to the main technique in order to accommodate for that. We certainly have the asymmetry of the returns, and we also have asymmetry in the tail dependence, i.e. the fact that large negative events tend to happen simultaneously, while large positive events are more idiosyncratic. So those are, in brief, like the key artifacts of how we can observe the financial returns to behave. And of course, this makes it very suitable to try to approach the modeling from the standpoint of time-subordinated models. And we of course know that all Levy processes can be represented as time-subordinated models. And that idea has been established by Clark and then shortly after by Mandelbrot, probably about 50 years ago. And why is it so attractive for financial applications? Because it's very intuitive. It's very intuitive, and it offers us a framework as to how to rebuild the standard modern financial theory that is based on Brownian motion into the world of fact-tails. And this intuitive concept comes from the fact that we can claim that the market returns indeed follow Brownian motion, but under a clock that is different than our physical clock. A clock that we call market timing clock. And the main concept is that when there is a lot of new information with regards to a given market, this market clock starts to tick faster compared to our physical time. And when there is no new information on the market, that market clock ticks slower compared to our physical time. i.e., it follows a stochastic process. And when we suitably choose this stochastic process, we can do this time-subordinated model, and we can achieve a plethora of potential modeling techniques stemming from that single idea. So, stylized representation of time-subordinated models, we have Z of t being Brownian motion, T of t the market timing process, and then R of t will be a Levy process under suitably selected T of t, and we know that each Levy process can actually be represented in that way. In financial applications, this will be in most often used in two ways, either for risk management purposes when we put this into a Monte Carlo simulation framework, or for derivatives pricing, i.e. for pricing more complex contingent claims products related to certain optionality in the future. When we speak about risk applications, it's important to understand that like the purest theoretical model will not work. And it will not work for practical reasons, such as, for example, the large dimensions that we need to operate in. So typically, even the smallest dimension space in order to model a typical financial portfolio will have more than 100 factors. Fitting Pareto stable distribution with all its parameters on 100 factors is a task impossible, at least to our knowledge. With all the corresponding dependence function and so forth. The other reason as to why we need certain relaxation from the pure theoretical models is because the tail index for each of those factors will be different. So we cannot just have, let's say, in the stable operation case, all the components of the vector to be represented by the same tail index, by the same alpha parameter. We need that to change. And that is rather important because it is what afterwards allows to really build efficient portfolios and to choose between the assets in such a way that we minimize the tail risk of the portfolios. So for that reason, the model that we've actually applied is of this structure. This is the first model that we've applied, which is again time-subordinated model. But we allow this W here that has that actually triggers the time subordination to be alpha stable random variable, of course with beta equal to 1, but different tail indices. And this is known as operator stable multivariate distribution. And on the top of it, we apply the so-called Arno-Garch models in order to capture the volatility clustering. So this has been like the starting point. Unfortunately, this model does not represent a model suitable for pricing derivatives. The underlying process will not be a semi-martingale. And we faced certain challenges in that regard, which we further down the road overcome by introducing the classical tempered stable model. So it's very similar structure, however, we modify the characteristic function so that we make the very tails a little bit thinner. So by introducing this component, the exponential component here, into the levy triplet. So you can see it's the typical one for the levy motion if this exponential component is not present. By introducing it, what happens is that we make the very tails of the distribution just a little bit thinner, so that at the end we have all the moments being finite, and in that way we can build option pricing models. There are other opportunities and other options how one can do that. The variance gamma process, the normal inverse Gaussian process, generalized hyperbolic process, those are all options on how to differently temper the tails of the distribution so that we can do the option pricing, so that we have semi-martingale at the end. So this model has been implemented on very large scale. It has been used by financial practitioners. Those models are also being used within the hedge funds industry for option pricing and so forth. So this more or less has become, I wouldn't say mainstream, but definitely something that the industry uses. So now, what are the next set of challenges that we need to overcome? The next set of challenges is first of all related to behavioral finance. And the situation is that within the realm of the finance, there are multiple anomalies, or the way we call them, financial economic puzzles, that are absolutely persistent. And no matter the evolution of the markets, we observe those phenomena for more than probably 75 years now. And the first one is known as dividend puzzle, and it basically represents the desire of the financial market participants to pay more for dividend, for high dividend paying stocks. If we hold a given stock, we should be irrelevant as to whether that stock pays out dividends or not, because we own the stock, and whether we will receive the dividend in cash or that dividend will be reinvested in the same company should be the same for us, more or less. Yet, financial market participants, they tend to value higher stocks that pay high dividends relative to price to earning ratio. Another such puzzle is the volatility smile puzzle. Out of money put options are priced much higher compared to at the money versions of that same option. i.e., that means that investors are willing to pay more in order to reduce potential downside risk. Equity premium puzzle. This is of similar nature, investors desiring to much higher risk-adjusted premium in order to invest in the stocks rather than bonds. And uncover interest rate parity puzzle is one that again is quite consistent, that high interest rate currencies tend to outperform, which is anomaly again. And basically you can build an arbitrage type strategy by buying high interest rates currencies, which will further appreciate in value according to this anomaly, and shorting in order to have zero capital strategy a currency with lower interest rate. So again, like absurd from the standpoint of view of economic thinking. So in the literature, there are a lot of explanations to each of those puzzles, and they can be inflation-related, tax-related, and so forth. What interests us, however, is there a unified theory according to which those puzzles disappear? i.e., can we think of consistent framework of the world where those puzzles are not puzzles anymore, we understand as to why that occurs. And the situation is that there are only two such theories being available. And the first one is the theory of behavioral finance, i.e. investors are not rational and they have their own subjective thinking on how the financial markets evolve. And they apply their own so-called weighting function to the empirically observed distributions of the market returns, i.e. their views about the markets are not identical to what is being observed. And then on the other hand, we have the more quantitative approach of explaining those puzzles, which is based on processes that have higher than normal probability of extreme events, which are also, that is quite important, time varying. So the tail parameter needs to change through time. And now, since the behavioral finance is kind of gaining a rapid adoption, why? Because it's very intuitive, but it is absolutely not quantitative. We need to try to build a bridge between the two so that to be able in a systematic way to fulfill investor desires. Behavioral finance is getting traction also because of the evolution of the financial markets and phenomena such as, for example, much higher proportions of the capital going into being invested subject to investor values, investments in art, investments in illiquid assets, investments in, let's say, climate-related technology and so forth. So from that perspective, this concept of having investor-owned probability weighting function becomes of importance. How are we going to otherwise establish an objective way to value something that is non-tradable? Right? You cannot observe that price process on the market at all. So that is why it's important for us to build this bridge between the quantitative finance and the behavioral finance. And to introduce the behavioral finance, it has two main concepts, the one I already mentioned, the probability weighting function, which basically is applied over the cumulative distribution function of the empirical cumulative distribution function that we observe on the market. And it has been studied by the renowned Tversky and Kahneman that it is such that typically a science, you can see shape studied in various research papers, but it basically assigns higher probability to the extreme events on both sides of the distribution with some asymmetry. So it's an A-shaped type of function and represents the risk aversion and the profit-seeking characteristics of the investor. So now, what Kahneman and Tversky, for which they received Nobel Prize, did is to define a specific type of this weighting function that you can see here, which, as I've mentioned, is applied on the space of the cumulative distribution functions of asset returns. But unfortunately, the proposal for how that weighting function, what kind of form this weighting function could be, is inconsistent with the rational dynamic pricing theory. So the resulting distribution is not of a form which we can use as increments of Levy process. We cannot form a semi-martingale, and we cannot price any kind of contingent claims based on such models. So it's only good from the behavioral standpoint. It has some other issues as well, like it doesn't transform well the central part of the distribution and doesn't modify the variance of the posterior distribution in a suitable way. So it only kind of speaks about details appropriately. In order to fix this defect, what we can do is to revert the problem. So we can say that we want the starting distribution to be infinitely divisible so that it's form Levy process. We want the end distribution, the posterior distribution, the distribution from the lenses of the investor to be infinitely divisible as well. And we want to deduct, based on these starting points, the weighting functions in such a way that that holds true. And it appears that there are several very nice options, some of them very easy to work with. And the one that I've used for the example here is based on the Prelec function which is defined in the form as you can see here. And what happens is that if we apply it to normal distribution to start with, ultimately we receive negative Gumbel distribution. Negative Gumbel distribution has all the properties that we wish, and we know how to price options. We know how to use it for, like, in the realm of building risk functions and constructing optimal portfolios. So this is one way as to how we can build that bridge. We have specific models afterwards that can transform everything from the standpoint of behavioral finance, as I mentioned, option pricing and so forth. So now what we can do is we can use this model, observe the options that are available on the market, and actually deduct what is the weighting function of the market participants. And in that way, we can visualize what are the behavioral biases of the market participants trading options at the moment, which we call market sentiment, extracting market sentiment. And this is like a small empirical example that we did based on that model. We can see that indeed the weighting function of the option market makers follows exactly the same shape as Kahneman and Tversky predicted, and based on that we can actually embed that sentiment afterwards into a portfolio construction process in order to see optimal weights according to those biases, which in many cases can be wisdom, not necessarily negative biases. And this is the second example from this part of the presentation that I wanted to share with you. We did optimal asset allocation between 3 regional indices, and we have found significant differences in the optimal weights between a model that simply uses, in this case, tempered stable distribution based on the empirical observations, and then the second optimal portfolio that uses this sentiment adjusted through the market participants weighting function model that I briefly described. And we actually see that the market, in this particular case, option traders do have wisdom because based on that sentiment, the optimal strategy will over-allocate based on sentiment into those indices that tend to appreciate in value in the following periods and vice versa. So this is like a brief overview of what we can do with regards to bridging the behavioral finance with the field of Levy processes. There is much more, and I can, to those who are interested, provide some further references as well. And the third topic that I wanted to touch upon is how we can use Levy processes for modeling exogenous risks. This is a topic of very high importance as of recently, why the pandemic was such an exogenous risk. There was no way how the market could have priced such an event within the prices that they form on the market. The Russian-Ukraine situation also exogenous risk that there was no way to price it. Climate risk is again something of similar nature. So it is now very well understood that the realm of financial markets is not an isolated place, and that we need to find mechanisms as to how to incorporate such exogenous factors when risk management is being considered. And I start this with the same picture in the beginning, this oversimplified picture of the main concept of market clock and turbulence, and from there time-subordinated processes that better explain the behavior of the financial markets with the extreme events, symmetry, tail dependence, and so forth. So now, what if we not only have one market clock that is responsible for all the news that are implicit to the financial markets, but we actually have several clocks that tick independently and are responsible for different type of news. One clock for climate-related news, one clock for political type issues, and so forth, which are now exogenous. We cannot extract them from the market prices as in the previous case. We need to find additional variables in order to model the intensity, observable variables, in order to model the intensity of those different clocks. And for a given industry that is significantly carbon intensive, that clock will need to tick much faster so that all that is being absorbed in one way or another, be it through carbon-related taxes or you name it, compared to another industry which is not carbon emissions intensive. So they will have different tail index related to the carbon intensity. And how can we do that? We can do that through multiple subordination of the original model. So we'll start subordinating factor by factor, layering in additional uncertainty based on each of those exogenous factors that we want to incorporate. Now, there are a lot of problems in the details of that, but that is the main concept here. And you can see the structure of the model outline. So we now have two, in this case this is double subordinated model, and we have, again, starting from a Brownian motion, B of t will apply to subordinators T of S, which is our standard market clock, and now we will have U of S, which will be our second subordinator, responsible, let's say, for carbon intensity. There are cases, again, in which this can work very well, and even numerically we can find even closed form solutions, like in the stable case, which I've outlined here. So it's immensely easy to do double subordination in the alpha stable case, and to offer you a glimpse of what we can earn from that empirically. Very natural way of shifting your optimal allocations, let's say, across industries, so that you have carbon-aware allocation. And in this particular case, we need to do one step more. We need to have at least one factor model for modeling each of the sectors. Factor will represent our overall market. The entire global economy has certain carbon intensity. that applies basically to all the sectors afterwards, but then the residual on the top of that is specific to a given sector. And by applying this double subordination based on the stable case, you can see the original tail parameter for each of the sectors, and you can see the carbon adjusted tail parameter for each of the sectors, so as well as the scale parameters. So no surprise, utilities become much more heavy-tailed when we do the second subordination, when we embed the carbon intensity as additional news external to the system that is coming. Energy, actually tail index doesn't change that much, but actually the scale explodes. It's a very important observation to make that because we are interested in optimizing across those sectors, the absolute level of the scale parameter doesn't matter. It is the relative scale that matters for us, right? So we should not be kind of misled by those numbers being different magnitude of the numbers here. That doesn't matter. It's the relative scale that matters. And when we do the optimal portfolio, we see that it achieves exactly what we would intuitively do, but now in a quantitative way, which actually means that we can apply the same for much more complex problems where intuition will not be enough. We have constraints here of minimum 3.5 in each given sector and maximum 35% in each given sector. And we see that this is optimal tail risk, i.e. conditional expectation minimization on the left tail. We see that we are reducing the weights in the utilities. Energy was on the bottom even in the original portfolio, so no change there. And we're increasing the weights in the communication services that are less carbon intensive and healthcare as well. So just to give you an illustration of how a relatively complex concept can be applied within the specifics of that kind of very important and practical needs that the market participants have to prepare their long-term portfolios for migrating to green economy. And when we speak about trillions of assets being invested, moves from one sector to another typically need to be planned years ahead so that to be executed efficiently. So in conclusion, what I would like to say is that contemporary markets are encompassing new and much more complex phenomena, and that even the main problem of modeling fat tails and turbulence is not that easy. We cannot just take a theoretical concept and apply it because of the specific additional phenomena of how the market returns behave. However, with certain relaxations from the purest models, we can still build very interesting and models that work in practice in order to accommodate for both behavioral aspects of the market participants as well as incorporating exogenous risks into the typical problems of derivatives pricing and optimal asset allocation. That concludes my talk. I would like to mention that within the buy-side strategy, I have a small team which is called Incubation Hub, where our objective is indeed to incubate novel ideas and then share with market participants in order to test them out and see what may have value. So I welcome everyone. If you see something within your realm that can answer any of those problems that I've identified briefly today, or any other applications in the world of finance, I welcome your sharing and look forward to potential future collaboration. Thank you.
Okay, thank you, Boriana, for so interesting presentation. Now some comments from the audience. Okay.
How do you validate your models and test the performance or maybe calibrate? Can you comment on that?
Yes, absolutely. That's an immensely important question. Typically, our models, first of all, we need to separate them out, and I will do by categorizing them in three. The first one is risk models. So within the risk models, there are three main risk measures that the market participants are used to work with. The first one is standard deviation. The second one is varied risk, which is basically a tail quantile function. And the third one is expected tail loss. That is the conditional tail, the mean of the conditional distribution. There are different techniques as to how to test. For standard deviation, we would use just out-of-sample backtesting, let's say with bias ratio estimation. For varied risk testing, there are several tests that can be used, whether there is, first of all, whether you're underestimating or overestimating the quantile value, but there are also tests with regards to, let's say, whether there is, you typically test for exceedances, whether the number of exceedances that you observe on this backtesting kind of within the backtesting process are consistent with, let's say, 1% hypothesis if you are testing for the 1% varied risk. But you can, and we should, and we do that. We test also for clustering of those exceedances, whether they're IID and so forth. So those are very standard kind of techniques that are available in like the regular statistics. We just apply them on our models. Then on the optimal portfolio, it's like a different realm. You just test again out of sample backtesting whether you have consistent outperformance of the optimal portfolios. It's very important to test it with different holding periods, with different horizons of the projections. It's massive, typically, in order to do. But from a mathematical standpoint, there is not that much interesting. Everything is available in the standard kind of statistical theory.
Okay, are you happy with these comments?
Yes. Also, it's interesting how stable are markets in the sense that will the future be similar to the present, the past?
Yes, that's a very, very important comment, and that is why, although I didn't emphasize, I did mention that that's another problem in the stylized way of a Levy process, let's say alpha stable Levy process, your tail dependency is constant. In the markets, it is not, it's dynamic. I've mentioned this briefly, so when I was speaking about the models that resolve those financial economic puzzles. That is why we cannot have the stylized, the purest form of those processes. We go to numerical kind of modifications, everything is Monte Carlo based and so forth. So it's not perfect.
Okay, some more comments. Okay.
Why is it necessary to do this double subordination to model these different intensities? Because just at first glance I thought that it should be sufficient to just take two different subordinators, add them to get another one, and then you are in the first model somehow.
How are you going to add them? Like you are adding them by making this convolution. You cannot just do the plus sign, right? So this is a convolution, exactly what we do. So it's the Brownian motion in the non-subordinated cases, just of t is the physical time. In single subordination, we do t capital of t, which is the market subordination, which we extract from the observable market prices. And now we do Brownian motion of u of t, And U of T is our second subordinator, which we fit, let's say, on carbon intensity, which is not priced in, like it's not embedded in the market pricing. We need an external variable. Does it explain it? Or?
Yeah, maybe
I'll send you the paper.
Okay. Yeah, please.
First, I would like to say that I highly appreciate your work.
Can you try on the microphone?
I highly appreciate your work. And I think that you can be very useful for the scientific society with imposing your problems. And would like to ask you how you take into account the long-range dependence.
Thank you for the process. None of these models that I shared today would take into account long-range dependence, but fractional Brownian motion, for example, can, and we now know how to modify it slightly, although I won't be able to speak details right now, in order to allow for it to be semi-martingale as well.
Okay. Some more questions or comments here? Okay.
Maybe this is quite a silly question, but you ever...
No silly, there are no questions are silly, so please go ahead.
Thank you. Do you see any potential to use triple subordination? Thank you for the talk about it.
Yes, exactly. So we need to overlay several such factors. Now there is an additional problem which I tried to avoid, but you didn't let me to. We need to find a way how to have a measure of the relative scale between those factors. But yes, in general, you can do triple subordination.
Thank you.
Which means that we have convolution, and from theoretical point of view, there is no restriction.
Exactly, yes. Yeah.
We
You
have
need
to
to find the data, however, appropriate data in order to judge the scale. There will be one more kind of constraint as to the relative scale of those subordinators.
Are there more questions? I personally like very much this like a statement that fat tails or heavy tail distributions are the new normal distribution. It's really a new world. And there is a lot of content behind this. And maybe the financial business was the area where people realized that there's something which is quite deep mathematically, but it is somehow useful for this or that specific area. This is my opinion. Okay, if no more questions, then let us applaud again. Do we need to wait?
No, maybe we can start.
Maybe, yeah. I believe we can start right now. No reasons to make any break. So we have our next speaker. It's Mr. Dragomir Medelchev. Let us ask him. Speaker.
Hello, everybody. At the beginning, let me thank the organizers for inviting me to talk on the topic of applying risk measures for the market risk. I'm going to present the results of a joint work with Svetlin Zaisky. And at the beginning, let me underline that I'm going to talk about risk measure, which has nothing to do with the probability measure, especially for people like you in the probability theory. The financial institutions like banks, funds, insurance companies, they are constantly exposed to various financial risks, like market risk, like credit risk, like liquidity risk, and so on and so forth. So these institutions have somehow to manage these risks. And the management of these risks includes taking and implementing various key decisions. And I'm going to talk about two key decisions to be taken by the financial institutions, like selecting the proper risk measure. And the second point is to select the proper financial model which describes the dynamics of the risk factors in question. Let me underline that the financial institutions are not free in making and implementing these decisions. They have to comply with internal factors and external factors. Internal factors are the decisions, the risk profile of stakeholders, the decisions taken by the compliance unit, the prompt correction actions issued by the internal audit, and so on and so forth. There are different internal players that somehow determine the decisions of the financial institutions. And these institutions have to comply. They have to take into account the expectations of the internal factors. And also there are external factors like supervisory bodies. Each nation has a supervisory body, and internationally there is such a body which is called Basel Committee of Bank Supervision, which is located in the city of Basel in Switzerland. This body adopts numerous acts, numerous decisions, and these decisions are obligatory for the banks and other financial institutions. And this is a brief description of the picture about the background in which the financial institutions operate and take decisions to manage the market risk. Market risk, this is the risk of sudden changes in the behavior of risk factors like asset price, like volatility, like liquidity, and so on and so forth. Do not mix the market risk with credit risk or other financial risks. So the first decision is which risk measure to select. And first of all, we have to dispose with a list of criteria to be met in order to consider a measure to be the proper risk measure. Such a list does not exist, actually. No, the decisions of the regulatory bodies are not transparent. They are not obliged to justify the decisions. They just unilaterally decide which is right, which is wrong, and so on and so forth. So this is why the decisions about the risk measure are actually based on interpretation of the acts and decisions of the regulatory bodies. And this is how the community decided that the risk measure has to be coherent. This is the first criteria for a risk measure. It has to be coherent. The coherence includes many aspects and includes also the so-called additivity. The additivity means that if we take two positions, the sum of the risk measure of the two positions has to be the same. And this is a key point for portfolio diversification and other activities by the financial institutions. If the risk measure is not properly selected, it might create wrong incentives for the financial institutions. And if a risk measure is not coherent, which means it's not additive, this might create troubles for the financial institution, for the whole sector, and also for the societies, and might generate political troubles. So this is why the risk measure has to be additive and to comply with other requirements to be coherent. But to be coherent is not sufficient for a risk measure. It turns out that the risk measure has to be also elicitable. Elicitability means that the risk measure has to be prone to forecast, to backtest, and so on, to play with the time. So why it is necessary to backtest the risk measure? Frequently and regularly, the bank supervision body checks the models of the bank. So, for example, now the bank, the supervisory body might check the models for the bank for the first half of the previous year. What does it mean to backtest the model? The model is calibrated, then outcome is generated, and because we have exactly what happened with these risk factors, we can easily check to what extent this model is reliable. And all this stuff is called elicitability. So there are two key criteria for a risk measure to be on the list. It has to be coherent and also elicitable. And I'm going to talk about these particular aspects of risk measures. And I'm going to compare the available risk measures and to talk about potentially new risk measure based on expected. Some 30 years ago, an investment bank named JP Morgan developed and adopted the value at risk as a risk measure. This measure actually indicates how much of your value is put at risk. So with a single number, you have a whole picture of your risk exposure. So it is very intuitive, by the way, easy to calculate, but also there are cons of this risk measure. It is very easy to manipulate, and also it is not additive. So since the value at risk is not additive, it is not coherent measure. So this measure generates strong incentives for the financial institutions, and this is why it is heavily criticized by the business community, by the academic society, and this contributed to the supervisory bodies looking for another risk measure. What is the value at risk? Actually, a value at risk is the quantile function taken with the opposite sign. And if we present the quantile through the CDF, this is the way to present it. Then I'm going to talk about 5 models. For 4 of these models, there is no PDF in closed form, and this is why we have to apply fast Fourier transformation to the characteristic function. And for this reason, at the bottom of the slides, you will see also the characteristic function for this measure in question. So this is the first risk measure. Traditionally, this is the measure used by the business community, but unfortunately, it is incoherent because it is subadditive, actually. So this is why the supervisors considered and introduced another risk measure, which is called expected shortfall. The expected shortfall, actually, this is the average value at risk. It takes into consideration the fat tails and also if there are chunks in the tails, which occurs frequently in the case of the financial markets. This is the way to express the expected shortfall through the characteristic function. The characteristic, the expected shortfall is relatively easy to calculate. It is not so intuitive. It needs to be interpreted. But the good news is that it is coherent. But it is not elicitable. So the Bank Supervision Committee actually moved from one trouble to another trouble. The value at risk, which is incoherent and elicitable, was replaced by this measure, which is coherent but not elicitable. And this creates a lot of troubles in the community. And to compensate the disadvantages of the 2 measures, actually the value at risk and the expected shortfall are implemented simultaneously for various reasons. When you have to backtest, you apply the expected shortfall. For other purposes, you use the value at risk as a threshold for the expected shortfall, and different various combinations between value at risk and expected shortfall actually is used. Why this happens? Because it was considered that there is no measure which is at the same time coherent and elicitable until the academic community came to the conclusion that there is such thing which is both coherent and elicitable, and this is the expected. The expected might be considered as an improved version, a better version of the quantile. In this equation, we see the way we can derive the quantile, and this is a leveraging of linear optimization problem. If we apply the optimization to the square of the same function, what we receive is the expectile. The quantile considers only one point on the curve, while the expectile considers 2 points. And for this reason, it takes into consideration the behavior of the two tails of the distribution, which is very good for the purposes of measuring and managing the risk. Another way to present the expectile is to, this is, by the way, one of the possibilities to calculate the expectile. This is the way to present the expectile. And the proposal that we are talking about is to use the expectile as the base for the new risk measure. And we are talking of expectile-based risk measure. And by analogy with the quantile, we take just the opposite sign. So this is why we change the sign within the expectation. And this new stuff, this new measure, is what I'm going to talk now. And the point is to compare the performance of the value at risk, expected shortfall, and expectile. Let me underline again that this risk measure, by definition, is both coherent and elicible. So currently there is a search, there is a hunt to invent the so-called ideal risk measure, which is both coherent and elicible. This might be the next stage of managing the market risk. Risk measure based on the expected. So this is the first part of the talk. I was talking about the decisions to be taken by the financial institutions how to measure the risk. Currently, there are only 2 risk measures, but a third one is on its way to the banking community. The next key decision by financial institutions to be taken is to select which models to use to describe the behavior of the risk factors. And I'm going to present to you 5 models for the following reason. Financial markets are characterized by several features which are called stylized facts. Actually, these stylized facts make the financial markets different from the other markets, but nevertheless, these facts are typical for the financial markets. The list of stylized facts evolves. New features are added. Some features are no more applicable, but nevertheless, there is a list of stylized facts. And about the quality of one model, you can judge based on how many stylized facts are covered by this model. And because there are numerous stylized facts, there are numerous financial models, because each model is designed and applied in order to capture certain stylized facts. For example, you're interested very much in the stochastic nature of the volatility. Fine. There is a multitude of models that capture the volatility, clustering, the leverage effect, and other stylized facts. If you're interested in the jumps, in the risk factors, fine. There is a multitude of models that capture the jumps and so on. So depending on the scope, depending on the field where you have to apply this model, you can pick up the proper model. But for this reason, you have to dispose with this multitude of models and to be aware of the pros and cons of each model. I will begin with the Black-Scholes model. This is the very basic model, and actually all other models to a certain degree present an improvement of this model. This model has a drift and a diffusion. Mu is actually the return, and sigma in this case is the volatility. So no stylized fact is captured by this model, but we need this model very much in order to find in which direction we need to improve this model, which stylized fact we would like to capture our model. The next model is the exponential temperance table. This model actually presents the dynamics of the asset returns by exponential of a process which is actually a temporal stable. So this model is deals with the jumps of the risk factors, and this is why it is designed, applied, and so on. You see that we are moving far from the very basic model like Black-Scholes, because, for example, we have to capture the jumps of the risk factor. This is the characteristic function for this model, which is used later through fast Fourier transform. These two models, the Black-Scholes and this model, the exponential tempered stable, the common denominator between them is that they consider the volatility to be constant. So they don't deal with the stochastic nature of the volatility. By the way, this is another stylized fact. We admitted a long time ago that the volatility evolves in packages, in different groups. You have to determine the change point when one package stops, when another package begins, and so on. But this requires that you develop and you apply a model which considers the volatility in its stochastic nature. So this is the first model for my talk, which considers the stochastic volatility. And actually, this is an improvement of the Black-Scholes model. We have the same drift. Again, the Brownian motion drives the stochastic nature of the process. But in this case, the volatility is described by a further equation. This is a Cox-Ingersoll-Ross model, which is mini version, by the way. So in the case of Black-Scholes, the volatility was constant, and here we consider the volatility to be described by this equation. This is the average. This is the mean to which the process reverts in mid-time period, and this is the speed by which the process reaches the mean. We have square root just to get only non-negative results, because the volatility cannot be negative and because the price of asset cannot be negative. Theta in this case is the volatility of volatility. It is up to you whether you can introduce another equation and present this volatility of volatility by another model. So this model is a little bit more complicated compared to Black-Scholes, because it considers the volatility in this way. Usually, the decisions of financial institutions are constrained by the trade-off, and the trade-off consists in the following. The more sophisticated is the model, the more stylized facts you capture, but the more parameters to be estimated. So you have to very strictly consider how many stylized facts you have to capture. Any additional complexity of the model will create unnecessary troubles with the calibration, and I will cover this point a little bit later with our empirical results. So for the first time of my talk, we are considering stochastic volatility. This is the characteristic function for the Heston model. The other model is Bates model. The Bates model actually uses, this is the Heston model, and adds one component for the jumps. So Bates model has been developed, and it is applied when you would like to capture two stylized facts, stochastic volatility and jumps of the risk factors. So theoretically speaking, for this reason, the model shall outperform, is expected to outperform the Heston model, but on the other hand, we have to calibrate 8 parameters. In the case of Heston, there were 5 parameters to calibrate. Here we have 8 parameters, and this is a major challenge to calibrate these models. Actually, this is the jump processes are captured by a compound Boltzmann process with intensity and jump sizes of this component of the model, and this is the way to present the log normal asset price. So we are already exposed to a very complicated model like Bates, and this is the stochastic function. So the fifth and the last model of my talk is a model which is very similar to Bates, but the jumps do not follow normal distribution, and actually they follow a Levy process of the type of temporal stable distribution, and this is for this reason, because we add this temporal stable instead of the normal distribution. In the case of the characteristic function for Heston, we have to add one component to take into consideration the jumps that follow temporal stable distribution. So far, this was the theoretical part of my talk. What I covered is the decision of how to select the proper risk measure. Is it possible to think of an expectile-based risk measure? And what are the models to use to apply this risk measure? This is the empirical side of my talk. As underlying asset, we consider the S&P 500 index. We consider the close price. This is the time period, enough observations, representative sample. We think moving window of this number of dates, and the calibration of the process was done. And these are the outputs of the empirical part. So what we see on the slide, I would underline two conclusions. In green color is Black-Scholes, by the way, and here we see the error of Black-Scholes. What can we say is that Black-Scholes actually underestimates the risk, and for this reason it is difficult to imagine that a supervisory body will approve your model if you apply Black-Scholes. But nevertheless, Black-Scholes is necessary as the floor against which to compare the other models. What we can also say is when we compare Bates with Heston, Bates captures two stylized facts, stochastic volatility and jumps, and for this reason we assume that the model will perform much better, but this is not the case. We see some periods where Bates overreacts to the market situation compared to Heston, and we explain this by troubles with the calibration. Actually, to calibrate it, parameters is a real challenge. The other slide deals is actually another slice of the empirical part. On the slide, what we see is a comparison of different risk measures, the empiric against the theoretical which we introduced. The key conclusion from this slide is that expectile-based risk measure performs quite well compared to the traditional measures like value at risk and expected shortfall, and for this reason, this measure can be considered in the future as to be introduced by the supervisors or by the business community, because the performance is quite acceptable compared to the traditional measures. In this respect, we contributed also to the academic stuff. The play with different risk measures is at which percentile to apply the measure. If you decide to apply quantile, the question is whether you are interested in 1%, 1 percentile, are you interested in 99 percentile, 99, 97.5, and so on and so forth. So this is a big game, by the way. And the same goes for expected shortfall. The big question is at which percentile we consider the expected shortfall. There is actually a quarrel, a discussion between the banking community and the banking supervisory bodies at which percentile to consider these measures. And the same goes for the expectile, at which percentile to take the expectile. In the case of our study, instead of playing with how much of the tail to consider, we introduced corrective coefficients. This is a kind of a multiplicator, and the application of this multiplicator, we think, solves this trade-off between the different percentiles to calculate the risk measures. And what we see here is that the corrective coefficients have been calculated correctly, and we find these results to be very satisfactory. Okay, so this is the end of my presentation, of my talk.
Okay, we are doing very well. Just in time, we have some 5-10 minutes for discussions. Do you have some comments? Near the microphone.
For the nice talk. My question is more comments than question. As far as I know, expectiles are a particular case of quantiles of the integrated tail distribution. Is it possible some subset to be improvement of all set? In my opinion, expectiles are just a subset of quantiles which possess very good properties. This is my opinion. If I am wrong, you can correct me.
Yeah, okay, can you make some comments?
Yes, you're right to make a parallel between expectile and quantile, and this was mentioned during the talk. What matters for the purpose, for the topic of my talk is that the expectile is both coherent and elicible. So these are the two criteria that we apply to each risk measure in order to consider or to ignore this risk measure. Since the expectile is both coherent and elicible, this perfectly matches our needs. Maybe in the future the list of criteria for a risk measure might evolve and new conditions will be added to the list. This will be, only in the future. The future will demonstrate. But for the time being, this is the perfect match for what the community needs. I'm not talking of the supervisors because it is not clear what are the expectations of the supervisory community. But for the purposes of, from the viewpoint of the banking community, this is the perfect risk measure based on expected.
Okay, but it is a subset of quantiles.
I would not rush to agree. These are different. Yes, the expectable might be expressed by quantiles and vice versa.
For another type of distribution.
Yes.
Another distribution, not the same.
Correct. There are distributions for which they coincide, and for the normal distribution, this is not the case. There are distributions derived, available, for which the expectile is so easy to be derived. Whether the expectile-based risk measure will depend on the adoption of these distributions instead of the normal one, this will be a decision by the supervisory bodies.
Can you? I'm not sure that microphone is working, but you can try, or you can hear everybody too.
I'm just curious. Is there a simple way to demonstrate that the expectile is a better risk measure, let's say, than a quantile? For example, if you have a portfolio of stocks and you want to combine it in the most efficient way, so to have the biggest return for a certain level of risk, can you demonstrate that the expectile leads to a better, more efficient portfolio? Also, or another simple criteria like this?
Okay. What matters for the banking community is whether this measure is additive and whether it is prone to forecast and backtest. And risk measure based on expected is both additive and realistic. You can forecast it, you can backtest it, and if you diversify your portfolio by investing in different positions, and you know the risk measure of each position, the risk measure for the portfolio will be just the sum of the risk measure for all positions. So this is what matters for the banking community. Two criteria: additivity and capability to forecast and backtest. But you raised another point. What are the consequences of moving to a new risk measure? Actually, this will change the acceptance set produced by the supervisory bodies. This will change also the portfolios and the portfolio optimization for sure. The expectal is used very much in the insurance industry. There are well-developed methodology how to apply it, and for sure this will change the risk management, the market risk management of the banks. And we as consumers of banking services, we will feel this change. The portfolios will be different, the market risk will be different, the price, the cost for managing this risk will be different, the capital adequacy will be different, managed in a different way. So many consequences will be there.
Hey, okay, maybe it is not surprising that there are different views to this or that notion, but it may happen that within one notion which is introduced, there is another one which is inside, which tells a little bit better to do this and this. But all this, for me, is a result of the freedom we have when building the models and trying to use them for answering some practical questions. Maybe now it's time to hear some comments from Doriana.
Yes.
Can you come here, please?
I think my
No. Come here, please.
Okay.
Yeah.
So just maybe to follow up on the previous comments. And by the way, thank you for the presentation. I enjoyed it very much. Thank you. Thank you. It's just a short comment. You can actually, you can't optimize on value at risk at all. So your problem will not be convex. So from that standpoint, you cannot contrast the optimal portfolio based on the new proposed measure with that of value at risk, as the latter simply does not exist. So it is in any event a much better measure as being a coherent one. So I just wanted to kind of make this comment that based on value at risk you cannot even have like good optimal portfolio, as the problem is not well defined.
Okay, thank you. Just let me add to the comment of the previous question. This is the way the three measures perform. And in the case of expected-based risk measure, we see sufficiently well performance. So the point is not whether it is better performance. Better performance, by the way, is nonsense. The point is to what extent these measures comply with the empirical calculations. And we see that three of them move as a package, move together, which means that the expected-based risk measure performs as well as the other measures. But it has one incomparable advantage. It is both coherent and both realistic.
Okay, is there somebody else wishing to make comments or to ask questions, some suggestion? Okay, let us thank the